The cosmos holds secrets that defy every scientific explanation. We are diving into the top 25 unexplained space anomalies, a collection of cosmic puzzles that have baffled the brightest minds for decades. By the end of this journey, you will know the most perplexing mysteries that are actively reshaping our understanding of the universe. Why did a single radio signal from 1977 never repeat? And what is the strange force pulling our entire galaxy towards an unseen horizon? What does it truly mean to look into the vast unknown and find only more questions staring back? On a quiet Ohio night in August 1977, a radio telescope known as the Big Ear was silently scanning the sky. It was a routine survey, one of countless nights of listening to the cosmic static. Then it happened. For 72 breathtaking seconds, a signal burst through the noise, so powerful and so perfectly aligned with what scientists predicted an artificial transmission would look like that it stunned the astronomer who found it. Jerry Amon printed out the data on a simple line printer, and in a moment of pure astonishment, he circled the alphanumeric sequence in red pen and wrote one word beside it: wow. That sequence, 6EQUJ5, was a measure of the signal's incredible intensity. It was 30 times stronger than the background noise of deep space, a sharp, focused shout in a universe of whispers. The signal appeared to originate from a region near the constellation Sagittarius, a point with no known stars or planets at the time. The immediate and enduring question was, what could possibly produce such a brief, brilliant, and targeted burst? The hunt for an explanation began almost immediately. Could it have been a reflection from a passing satellite or a piece of space debris? That possibility was quickly ruled out, as no known human-made object matched the signal's specific frequency and behavior. Others proposed a natural cosmic event, perhaps a comet's outburst or an unknown stellar flare. Yet decades of searching that same patch of sky have never found a repeating phenomenon or a natural explanation that fits all the evidence. The signal's unique properties, its narrow bandwidth, and its apparent origin from a fixed point in interstellar space keep the most tantalizing theory alive, that it was a one-time transmission from an intelligent civilization. Why has it never been heard again? This is the heart of the mystery. Countless projects have aimed their dishes at that exact coordinate, listening for a follow-up, a repeat, anything at all. They have heard only silence. The wow signal remains a solitary event, a single, perfect note played in an empty concert hall, leaving us to wonder who or what was the composer. It stands as a monument to our search for cosmic company, a ghost in the machine that continues to haunt the science of SETI, the search for extraterrestrial intelligence. While the wow signal was a fleeting shout in the radio silence, another mystery announced itself with a persistent, rhythmic flicker. In the constellation Cygnus, a star named KIC 8462852, but known to the world as Tabby's star, began behaving in a way astronomers had never seen. The Kepler Space Telescope, designed to hunt for planets by spotting the tiny, regular dips in starlight they cause, found something entirely different here. The light from this star did not dip by a mere fraction. It plummeted, sometimes by as much as 22%, in massive, irregular, and utterly chaotic blocks. This was not the signature of a planet, which would cause a gentle, repeating dimming. This was as if something colossal and shapeless was passing in front of the star, something on a scale that defied any natural explanation we could conceive. The strangeness was so profound that scientists were forced to consider every possibility, even the most extraordinary. The most famous hypothesis suggested we might be witnessing the construction of a Dyson sphere, a hypothetical alien megastructure designed to encircle a star and harvest its energy. The idea captured the public imagination, a vision of a civilization so advanced it could build on a stellar scale. It was a compelling, if startling, answer to the question of what could possibly block that much light in such a jagged, unpredictable pattern. The allure of this explanation highlighted just how bizarre the data truly was. Of course, astronomers diligently searched for more conventional answers. The primary natural theory involved a vast, swirling swarm of comets, perhaps disturbed by a passing star, creating a thick, irregular cloud of ice and dust. Others proposed a circumstellar debris disk, a ring of planetary building blocks that was somehow clumpy and uneven. Yet each of these explanations faced significant challenges. A comet swarm large enough to cause such extreme dimming would require an implausibly vast number of comets, and the dust from such an event should have generated a clear infrared signature which was largely absent. The debris disk theory struggled to account for the sheer depth and irregular timing of the dimming events. Years of intense observation have followed, and Tabby's star continues to be an enigma. We now know it is also undergoing a long-term secular dimming, fading slowly over the course of years, a phenomenon that adds yet another layer to the puzzle. While the alien megastructure idea remains a remote and speculative last resort, the true nature of the obstructions remains unknown. It is a cosmic detective story where every clue leads to more questions, forcing us to question our fundamental understanding of star systems and what is possible within them. This star stands as a testament to the fact that sometimes the most profound mysteries are not brief signals, but long, slow dances of shadow that we are only just beginning to see. From the chaotic flickering of a distant star, we travel to a structure of unsettling geometry. Suspended in the darkness some 2,300 light-years away is a cosmic object that seems to defy nature's preference for curves and spheres. It is called the Red Rectangle Nebula, and it is exactly what its name suggests, a vast, glowing red shape with corners so sharp it looks manufactured. This is not an artist's impression or a trick of perspective. It is a real nebula displaying a symmetry and angularity that astronomers struggle to comprehend. At the heart of this crimson puzzle lies a binary star system, two stars locked in a tight orbital dance. The prevailing theory suggests that as one of these stars nears the end of its life, it is expelling its outer layers into space. But instead of forming a billowing, spherical cloud, these ejecta are being funneled into two opposing cones of gas and dust by the powerful gravitational tug of war between the two stars. From our vantage point on Earth, we are looking directly at the base of these cones, creating the illusion of a near-perfect rectangle. It is a cosmic hourglass with its waist pinched by stellar forces. Yet this elegant explanation only deepens the mystery. The mechanism that sculpts the material into such perfectly straight lines and crisp 90-degree corners remains unknown. Natural phenomena tend to create diffuse edges and soft blobs, not sharp vertices. What physical process is acting as a cosmic stencil, ensuring the dust and gas conform to such a rigid geometric shape? The nebula's profound redness adds another layer of intrigue. This intense glow comes from a class of complex carbon-based molecules known as polycyclic aromatic hydrocarbons, which are being excited by the intense ultraviolet light from the central stars. These molecules are common in space, but here they exist in such unusual abundance and under such specific conditions that they create a spectral signature unlike any other. The red rectangle is more than just a pretty shape. It is a chemical factory producing organic compounds in a structure that feels impossibly precise. It challenges our assumptions about how matter behaves in the depths of space, presenting us with a beautiful, blood-red geometric proof that the universe still holds designs we are only beginning to perceive. The stark geometry of the red rectangle feels almost architectural, a shape that seems designed. But what happens when an object from beyond our solar system appears, bearing a form that defies all our expectations? That is precisely what occurred in October 2017, when the Pan-STARRS telescope in Hawaii spotted a faint point of light moving at unprecedented speeds. It was the first visitor ever detected from interstellar space, and it was given a name that means scout or messenger from the distant past in Hawaiian, Oumuamua. From the moment it was discovered, Oumuamua was an outlier. Its path was hyperbolic, meaning it was not bound by the sun's gravity and was merely passing through on its way back out into the galaxy. But its most striking feature was its shape. Based on the extreme variations in its brightness as it tumbled through space, astronomers deduced it was highly elongated, perhaps 10 times as long as it was wide. This cigar or pancake-like form was unlike any asteroid or comet we had ever seen in our own solar system, where such extreme proportions are unheard of. Then came the real mystery, its acceleration. As Oumuamua sped away from the sun, its trajectory could not be explained by gravity alone. Something was giving it an extra push. For a normal comet, this is easily explained by outgassing, when solar heat vaporizes ice on the surface, creating jets of gas that act like a natural rocket engine. But Oumuamua showed no visible coma, the fuzzy cloud of gas and dust that always surrounds an active comet. Our telescope saw a completely barren, rocky-looking surface with no signs of outgassing whatsoever. So what invisible force was propelling it? The scientific debate ignited immediately. One leading theory proposed that Oumuamua was a fragment of a Pluto-like world from another star system, a chunk of solid nitrogen ice that was chipped off in some ancient cosmic collision. As it passed near our sun, the nitrogen would have sublimated, turning directly from a solid to a gas, providing the thrust without creating the dusty coma that water ice would. This was a compelling natural explanation, yet it required a very specific and rare composition to work. The absence of that telltale coma, however, left the door open for more speculative ideas. The most famous, proposed by Harvard astronomer Avi Loeb, was that Oumuamua could be a piece of advanced alien technology, perhaps a light sail, a vast, thin sheet designed to be pushed by the radiation pressure from starlight. Its unusual shape and the fact that it gained speed without any visible exhaust seemed to some to fit this extraordinary possibility. The scientific community largely favors a natural origin, acknowledging that we are simply seeing a new type of object for the first time. But the very fact that the artificial origin hypothesis had to be seriously considered underscores just how strange this visitor truly was. Oumuamua is now gone, a silent wanderer back in the interstellar void, leaving behind a trail of questions that fundamentally challenge our classification of the building blocks of the cosmos. It was a messenger, all right, but the message was that the universe is capable of producing wonders we do not yet understand. Oumuamua's silent passage raises a question far bigger than one strange object. If the universe is so vast and ancient, filled with countless stars and planets, why does it feel so profoundly empty? This is the heart of the Fermi Paradox, a simple question with devastating implications. Where is everybody? The physicist Enrico Fermi first voiced this thought over lunch in 1950, looking from the sheer number of stars to the complete absence of any visitors. The math is overwhelmingly on the side of life. There are hundreds of billions of stars in our galaxy alone, many with planets in the habitable zone where liquid water could exist. Given that the galaxy is over 13 billion years old, there has been more than enough time for intelligent civilizations to arise, develop interstellar travel, and spread across the entire Milky Way. The silence we hear, the blank pages of our astronomical observations, stands in stark contradiction to this optimistic calculation. So what is stopping them, or perhaps stopping us? One of the most sobering answers is the Great Filter hypothesis. This idea suggests that at some point in the evolution of life, from non-living chemistry to a spacefaring civilization, there is an incredibly difficult barrier, a filter that almost every potential civilization fails to pass. The terrifying part is we do not know if this filter is behind us or still ahead. If it is behind us, it could be that the jump from simple single-celled life to complex multicellular organisms is astronomically rare. That would mean while microbial life might be common, animals, plants, and intelligence are virtually non-existent. But if the great filter lies in our future, it paints a much darker picture. It could mean that all advanced civilizations inevitably destroy themselves upon discovering certain technologies, perhaps through nuclear war, engineered pandemics, or a runaway artificial intelligence. Our own continued existence would then be a race against a clock we cannot see. Other theories offer less grim but equally strange possibilities. The zoo hypothesis proposes that advanced civilizations are fully aware of our existence, but have chosen to isolate us in a kind of cosmic wilderness area or a laboratory, observing our development without interference until we reach a certain level of maturity. Another idea is that the universe is simply too big and the timescales too vast for civilizations to overlap in a meaningful way. Imagine two ships passing in the night on an ocean that spans continents, one setting sail just as the other is sinking, their journeys separated by millions of years. Or perhaps the answer is even more fundamental, that we are simply not listening correctly. We search for radio signals, but a civilization only a few centuries more advanced than us might view such technology as we view smoke signals, a primitive relic they abandoned long ago. Their methods of communication could be as far beyond our understanding as the internet is to a Stone Age tribe. The Fermi Paradox forces a profound humility upon us, challenging not just our science but our place in the cosmos. Are we the first, the last, or simply the only ones to have made it this far? The silence is not just an absence of sound, it is a mirror reflecting our own unanswered questions. The profound silence contemplated by the Fermi Paradox is a mystery of absence, but some cosmic puzzles reveal themselves through a strange and undeniable motion. Astronomers have discovered that entire clusters of galaxies, on the very edge of our observable universe, are streaming in a coherent flow towards a single point in the cosmos, a phenomenon they call dark flow. This is not the random drift of cosmic expansion, but a directed, river-like movement of unimaginably large structures, all pulled by a force we cannot see. The visible matter and even the dark matter we have mapped in our universe cannot account for this colossal tug. It is as if an invisible hand is guiding these galaxies on a course we cannot explain. The leading hypothesis for this mystery is as staggering as the observation itself. Some scientists propose that the gravitational source of the dark flow lies beyond our cosmic horizon, outside the bubble of space and time we can possibly observe. This would mean the gravitational pull is coming from a vast accumulation of matter that lies in a region of the universe that has been forever separated from us by the finite speed of light and the relentless expansion of space. We are feeling the ghostly pull of something we can never see. Another, even more mind-bending possibility is that this flow is a remnant from a previous cosmic epoch, a scar left over from before the Big Bang, from a time when the entire structure of reality was different. This flow would be a cosmic fossil, a directional memory imprinted on the fabric of the universe during its first moments. The very existence of dark flow remains a hotly debated topic in cosmology. Its detection relies on subtle measurements of the cosmic microwave background, the leftover heat from the Big Bang, and some analyses have challenged the original findings. Yet, if it is real, it points to a fundamental incompleteness in our understanding of the cosmos. It suggests that the distribution of matter in the universe is not uniform on the largest scales, or that our universe is part of a much larger, and perhaps infinite, multiverse where the gravity from other universes can subtly influence our own. This mysterious current challenges the cosmological principle, a cornerstone of modern astronomy which states that the universe should look roughly the same in every direction. Dark flow hints that on the grandest scales, the universe may have a preferred direction, a vast, invisible slope down which galaxy clusters are silently sliding. This invisible river of galaxies, the dark flow, hints at a cosmos far more structured than we ever imagined. but we do not need to look to the edge of the observable universe to feel an inexplicable pull. Our own Milky Way galaxy, along with its local group and thousands of others, is caught in a relentless cosmic current, all flowing toward a single, mysterious point in the darkness. Astronomers call this the Great Attractor, a gravitational anomaly of such immense power that it defies our attempts to see it directly. The heart of this mystery lies in the direction of the constellation Centaurus, a region of the sky that is, from our perspective, completely obscured. This is the zone of avoidance, a swath of space hidden behind the dense bulge of stars, gas, and dust at the center of our own galaxy. It is like trying to see a distant city from the middle of a blinding fog bank. The very thing we are trying to study is blocked by our own cosmic backyard. For decades, this was a profound frustration. We could measure the velocity of our galaxy, we could feel the pull, but we could not see what was doing the pulling. The breakthrough came not with optical telescopes, but with instruments that could peer through the cosmic fog. Using radio, infrared, and X-ray astronomy, scientists began to map the hidden structures behind the Milky Way's core. They discovered that the Great Attractor was not a single, unimaginably dense object, but rather the core of a colossal supercluster of galaxies, the largest structure we have ever identified ourselves as being a part of. This is the Laniakea supercluster, a Hawaiian word meaning immense heaven. Laniakea is a cosmic filament, a vast web of hundreds of thousands of galaxies all bound together by gravity, spanning over 500 million light-years. Our Milky Way resides on a remote suburban fringe of this immense metropolis, slowly drifting toward its downtown core, the Norma cluster. This discovery was a monumental shift in perspective, redefining our cosmic address. Yet, even with this grand picture, the mystery has only deepened. The gravitational pull we feel from the center of Laniakea is powerful, but calculations show it is still not nearly enough to account for the full strength of the attraction. There seems to be a hidden source of mass, an excess of gravity that remains unaccounted for within the Great Attractor region itself. What is generating this extra pull? Is it an immense concentration of dark matter, the invisible glue that holds galaxies together? Or are there even more galaxies hidden within the zone of avoidance, a hidden metropolis we have yet to fully census? The true nature and total mass of the Great Attractor remain elusive, a ghost in the machine of our local universe. We are like sailors who can feel the current and have mapped the distant shore, but still cannot identify the powerful, submerged magnet that draws us ever onward. A gravitational pull from a hidden cosmic metropolis is one thing, but a force acting on our own robotic explorers is another. Decades ago, as the Pioneer 10 and Pioneer 11 spacecraft ventured beyond the asteroid belt, a subtle anomaly began to appear in their trajectories. These two deep space probes, having completed their missions to Jupiter and Saturn, were on their way out of the solar system, yet navigators on Earth noticed something was wrong. Both spacecraft were slowing down slightly more than predicted by the gravitational calculations of Newtonian physics. An unknown, incredibly faint but persistent force seemed to be tugging them back toward the Sun. This tiny, unexplained deceleration became known as the Pioneer Anomaly, a constant sunward pull of about 10 billion times weaker than the gravity we feel on Earth. For years, this minuscule drift defied explanation, creating a nagging worry that our understanding of the fundamental laws of motion, the very rules that govern the cosmos, might be incomplete. The most tantalizing and frightening possibility was that this was a sign of new physics. Could gravity behave differently over vast distances than our equations predicted? The mystery captivated physicists and astronomers for nearly 3 decades, a ghost in the machine of our own creation. The eventual solution, however, was not found in rewriting the laws of physics, but in the mundane reality of heat. These spacecraft were powered by radioactive thermoelectric generators, which produced a significant amount of waste heat. scientists realized that this heat was not radiating away from the probes perfectly evenly. A tiny anisotropic emission of thermal photons, essentially light particles, was bouncing off the back of the spacecraft's main antenna dish. Each photon carried a minuscule amount of momentum, and as it was emitted, it acted like a gentle but continuous brake, pushing the spacecraft back toward the sun. It was the spacecraft's own warmth, a byproduct of their power source, that was creating the anomalous deceleration. The mystery was largely solved. Yet, even with this elegant thermal explanation, some residual questions linger. The precise modeling of this thermal recoil force is incredibly complex, and some analyses suggest that it might not account for the entire effect with 100% certainty. A tiny fraction of the anomaly may remain unaccounted for, a whisper of a discrepancy that keeps a sliver of doubt alive. This lingering uncertainty serves as a powerful reminder of how difficult it is to model every physical interaction, even for something we built ourselves. It underscores the constant challenge of distinguishing between an engineering oversight and a fundamental discovery. The pioneer anomaly teaches us that sometimes the greatest cosmic mysteries are not found in distant galaxies, but in the subtle, unexpected behavior of our own messengers as they sail into the void. The gentle push of thermal photons on our pioneer probes showed how mysteries can hide in plain sight, but far beyond their path lies a boundary that makes no sense at all. Out past the orbit of Neptune, the solar system does not simply fade into the dark. It is home to the Kuiper Belt, a vast donut-shaped field of icy leftovers from the planet-building era, containing everything from tiny pebbles to dwarf planets like Pluto. For millions of these frozen worlds, this should be their domain, stretching steadily outward. Yet, at a distance of about 50 astronomical units from the Sun, something startling happens. The number of objects does not gradually thin out as you would expect. Instead, it plummets. This is the Kuiper Belt Cliff, a sudden and dramatic drop-off in population that current models of our solar system's formation cannot account for. It is as if you were walking through a dense forest that abruptly ends at a straight, razor-sharp edge, with nothing but empty plains beyond. This cliff presents a fundamental architectural puzzle. Why would the primordial disk of material that formed the planets just stop so abruptly? One of the most compelling theories points to a hidden architect, a massive, unseen planet whose gravity has shepherded the outer solar system. This hypothetical planet 9, a world potentially 10 times the mass of Earth orbiting far beyond the cliff, could be the invisible hand. Its immense gravitational pull would have swept through the ancient Kuiper Belt, violently ejecting a vast population of objects into deep space or hurling them inward, leaving behind only this stark, truncated edge as evidence of its past influence. We have not found this planet yet, but its potential gravitational signature is written into the strange emptiness at the solar system's fringe. Another, even more dramatic possibility involves a stellar intruder. Billions of years ago, when our Sun was still in its natal star cluster, a passing star could have ventured dangerously close to our infant solar system. The gravitational tide from this close encounter would have been catastrophic, stripping away the outer reaches of the Kuiper Belt in a single cosmic event, stealing a huge portion of our solar system's icy material and leaving behind this sharp cliff as a permanent scar. Each of these theories has its complications. Finding Planet 9 has proven extraordinarily difficult, and a stellar flyby is a one-time event that requires a very specific and perhaps unlikely set of ancient circumstances. Yet the cliff itself is undeniably real, a silent testament that our solar system's history is far from fully written. It forces us to question whether our cosmic neighborhood is truly quiet and orderly, or if it was shaped by a dramatic, violent event whose evidence is frozen in this distant, icy borderland. The Kuiper Belt Cliff suggests a hidden structure in our own solar system, but what happens when we find a galaxy that seems to be missing its most fundamental component? Dark matter is the invisible skeleton of the cosmos, the gravitational glue that holds galaxies together and dictates their very formation. We have never seen it directly, but its gravitational influence is written into the rotation of every spiral galaxy and the bending of light across the universe. It is considered non-negotiable, an essential ingredient in the recipe for a galaxy. That is why the discovery of NGC 1052DF2 sent such a violent shockwave through astronomy. This faint, ghostly galaxy, larger than our own Milky Way but containing only 1/200th of the stars, appears to have almost no dark matter at all. Its stars are moving at a sedate, leisurely pace, their velocity perfectly explained by the gravity of the visible matter alone. There is no extra pull, no missing mass, no shadowy presence. It is a galaxy built from only the parts we can see, a cosmic heresy that challenges everything we thought we knew. The immediate reaction was one of profound disbelief. Skeptics argued that the distance to the galaxy must have been miscalculated, throwing off the mass measurements. Others proposed that perhaps we are viewing it from a strange angle, or that its dark matter was somehow stripped away in a violent encounter with a neighboring galaxy. Yet follow-up observations have only hardened the initial findings, and more of these dark matter-deficient galaxies have since been identified. The anomaly is real, and it has ignited a fierce debate with two opposing sides, each with staggering implications. On one side, some scientists argue that galaxies like DF2 are the death knell for the entire concept of dark matter. They propose that our theory of gravity itself, Einstein's general relativity, must be modified on galactic scales. This idea, known as modified Newtonian dynamics or MUND, suggests that gravity works differently when its pull becomes extremely weak, creating the illusion of dark matter without it actually existing. For MUND supporters, DF2 is a perfect vindication, a galaxy where the modified laws perfectly predict the observed motions without any need for invisible particles. For the vast majority of cosmologists, however, who are convinced of dark matter's existence, DF2 is not a refutation but a profound puzzle. They are forced to ask, how could a galaxy form without the gravitational scaffolding of dark matter to pull it together in the first place? One leading theory suggests these oddballs are tidal dwarf galaxies, formed from gas and stars ripped away during a cosmic collision between two larger galaxies. Since this material comes from the outer disks of the parent galaxies where dark matter is sparse, the new galaxy would naturally inherit very little of it. Another possibility is that feedback from intense star formation or supermassive black holes somehow blew the dark matter away, a process we do not yet understand. This cosmic contradiction forces us to confront the limits of our models. If dark matter is real, its behavior must be more complex than a simple, uniform halo surrounding every galaxy. If it is not real, then we must rewrite the laws of physics. NGC 1052DF2 is more than a celestial curiosity. It is a stark reminder that even our most foundational ideas about the universe are still being written in the stars. While we debate the nature of galaxies, a more intimate mystery unfolds right next door on the rust-colored plains of Mars. The story of Martian methane is one of fleeting whispers and frustrating contradictions, a gas that appears and vanishes with no clear pattern. For decades, our robotic emissaries have been sniffing the thin Martian air, and their reports are maddeningly inconsistent. The Curiosity rover, for instance, has recorded sudden, dramatic spikes of methane, where concentrations soar to 10 times the background level, only for the gas to completely dissipate within a matter of days. Other orbiters and landers have sometimes detected it and sometimes found nothing at all. This intermittent, unpredictable behavior is the core of the puzzle. On Earth, methane is a powerful biosignature. The vast majority of it in our atmosphere is produced by living organisms, from microbes to livestock. When methane appears without an obvious geological source, it is a tantalizing, though not definitive, flag for biology. So when our instruments on Mars catch a whiff of this simple gas, the immediate and thrilling question is, are we smelling the breath of Martian microbes? Could there be subterranean colonies of organisms hidden deep in aquifers or within porous rock, producing this gas as a byproduct of their metabolism? The possibility that we are detecting the faint chemical signature of life is what gives this mystery its profound weight. Yet the universe rarely makes things so simple. Methane can also be created through purely geological processes, completely independent of life. The gas can be locked away in ice like structures called clathrates, released slowly over time by the warming of the Martian soil. It can also be produced by a reaction between water, carbon dioxide, and certain types of rock like olivine in a process known as serpentinization. The challenge is that from hundreds of millions of miles away, we cannot yet distinguish between a biological burp and a geological sigh. The evidence is tantalizingly ambiguous. The short lifespan of the methane plumes is a major clue. Mars has a very active atmosphere and is constantly bathed in ultraviolet radiation from the sun, which quickly breaks down methane molecules. For the gas to appear in such sharp, concentrated spikes, it must have been released very recently and very locally. This points to an ongoing, active source somewhere near the rover's path in Gale Crater and potentially other sites across the planet. But what is that source? Is it a slow, steady seep from an underground reservoir that only becomes detectable when atmospheric conditions are just right? Or are we seeing the result of sudden, small-scale geological events? Some scientists have even proposed that the methane is not native to Mars at all, but is being delivered by the constant rain of micrometeorites rich in organic compounds that vaporize upon hitting the thin atmosphere. Each new dataset seems to deepen the mystery rather than solve it. The European Space Agency's Trace Gas Orbiter, a spacecraft specifically designed to conduct a precise census of the Martian atmosphere, has repeatedly reported finding no methane at all, creating a direct conflict with the rover's ground-level observations. This contradiction could mean the methane is so localized and transient that the orbiter simply misses it, or that something on the rover itself is producing the gas, though extensive testing has largely ruled that out. The central puzzle remains unsolved, a cosmic tug-of-war between two equally compelling narratives. One story paints Mars as a geologically active but ultimately dead world. The other allows for the breathtaking possibility that we are not alone, that life, in its most basic and tenacious form, has taken root on the planet next door. Until we can bring samples back to Earth or send more advanced laboratories to the Red Planet, the methane of Mars will continue to be a ghostly signature, a question mark written in a gas we cannot quite pin down. While we search for signs of life on Mars, a perfectly geometric storm rages at Saturn's north pole. This is the Saturn Hexagon, a colossal six-sided jet stream that could swallow 4 Earths whole, and it has been spinning there for decades, perhaps even centuries. It is a hurricane of impossible geometry, a figure so precise it looks drawn by a cosmic compass. Nothing else like it exists in our solar system. The hexagon is a wave pattern, a standing wave frozen in the atmosphere, carving out the boundary between different bands of raging winds. Scientists have recreated similar shapes in the lab by spinning fluids at different speeds, showing that under the right conditions, turbulence can self-organize into polygons. But these laboratory versions are fleeting and small-scale. On Saturn, the hexagon is a permanent planetary-scale feature, a stability that defies our simple models. The underlying physics that locks this pattern in place, maintaining its sharp corners against the chaos of a gaseous giant's atmosphere, remains one of the great puzzles of planetary science. What is it about Saturn's deep atmosphere, its rotation rate, or its internal heat that provides the perfect recipe for this enduring shape? The hexagon is more than a beautiful curiosity. It is a natural laboratory for fluid dynamics on a scale we can never hope to build, forcing us to question how well we truly understand the flow of matter and energy in the most extreme environments. The perfect hexagon of Saturn is a monument to order, but the universe also holds patches of profound and inexplicable cold. Deep within the faint afterglow of the Big Bang itself, a cosmic chill defies easy explanation. This is the cosmic microwave background cold spot, a vast and unusually frigid region in the ancient light that fills all of space. The cosmic microwave background is the remnant heat from the birth of the universe, a snapshot of the cosmos when it was just 380,000 years old. It is remarkably uniform, a tapestry of minute temperature fluctuations that correspond to the seeds of all future structure, the galaxies and clusters we see today. But in this tapestry, one patch stands out. The cold spot is enormous, nearly 1 billion light-years across, and its temperature is significantly lower than the surrounding areas. This is not just a random variation. Its size and coldness make it a statistical anomaly so extreme that it challenges our standard model of cosmology. The probability of such a feature appearing by random chance is incredibly low, estimated at less than 1 in 200. So what could create such a colossal cold spot in the fabric of the universe? The most straightforward theory proposes a cosmic nothingness on an unimaginable scale. This idea suggests the cold spot is a supervoid, a region of space that is largely empty of both galaxies and the dark matter that binds them together. As light travels through such a void, it loses energy climbing out of the underdense region's gravitational well, a process known as the integrated Sachs-Wolfe effect. This energy loss would cause a slight cooling in the cosmic microwave background radiation we observe from that direction. The problem is one of scale. For a supervoid to cause the observed cooling, it would need to be so vast and so utterly empty that it strains our understanding of how structure forms in the universe. We have indeed found a large void in that general direction, but it is not nearly large or empty enough to account for the profound cold we see. The mismatch between the observed void and the required void is a major point of contention, leaving scientists to wonder if a simpler explanation is even possible. This failure of the simple void theory has opened the door to far more exotic possibilities. One of the most mind-bending hypotheses is that the cold spot is a bruise, a cosmic imprint from a collision with another universe. In the multiverse theory, our universe is just one bubble in a vast cosmic foam of other budding universes. If a neighboring universe had bumped into ours in the distant past, the energy transfer from that collision could have left a specific cold signature on our cosmic microwave background. The cold spot would then be direct, albeit highly speculative, evidence that we are not alone in the greater multiverse. Other physicists have proposed equally radical ideas, such as a giant knot in the fabric of spacetime itself, a topological defect left over from the universe's rapid inflationary phase. The cold spot remains an active and heated area of research because it is more than just a curiosity. It is a direct challenge to our understanding of the universe's infancy and its large-scale structure. Is it a statistical fluke, a cosmic illusion we are misreading? Is it evidence of a supervoid so immense it rewrites the rules of structure formation? Or could it be the first tangible clue that our universe is part of a much grander and more crowded cosmic reality? This enigmatic patch of cold sky continues to fuel our deepest questions about the nature of everything. Years after its initial discovery, the star that ignited talk of alien megastructures is still under the most intense scrutiny science can offer. The latest eyes on the mystery belong to the James Webb Space Telescope, and its unprecedented data is reshaping the narrative. Webb's powerful infrared instruments were aimed at Tabby's star, not to look for the shadows of giant structures, but to analyze the composition of the material causing the dimming. The results were decisive. The light-blocking material shows a clear signature of fine, microscopic dust particles. This finding effectively rules out a solid, opaque megastructure which would not produce such a spectral fingerprint. The alien construction hypothesis, while a thrilling thought experiment, has largely been retired by the hard evidence. So if it is not a Dyson sphere, what is it? The current leading theory points to a vast, lopsided cloud of dust orbiting the star. This is not a uniform ring, but a clumpy, asymmetric swarm, perhaps the remnants of a shattered moon or a catastrophic planetary collision. The irregular dimming patterns occur as this uneven cloud of debris drifts in front of the star from our perspective, its dense knots and sparse voids creating the chaotic blocks of shadow we observe. This explanation fits the data well, but it immediately raises another question. Why is there so much dust? Fine dust particles should not survive for long in such an environment. The intense radiation pressure from the star's light should push them away, clearing the inner system over a relatively short astronomical timescale. The very presence of this dust implies it is being replenished continuously, perhaps from the grinding collision of larger bodies in a persistent asteroid belt, or from the slow disintegration of a giant comet trapped in a peculiar orbit. The mystery has therefore evolved, transforming from a question of what is blocking the light to a puzzle of how such a strange dust cloud formed and is maintained. This dynamic nature is what keeps scientists hooked. The story of Tabby's star is a real-time demonstration of the scientific process in action, a mystery that changes form with every new observation. And this brings us back to the public's enduring fascination with the alien megastructure idea. Why does that speculative explanation persist in our imagination long after the data has moved on? It speaks to a deeper human longing, a desire for the cosmos to be not just strange but inhabited. A dust cloud is a natural, if peculiar, phenomenon. An alien megastructure is a story, a testament to a universe teeming with intelligence and ambition. The star's true anomaly may not be in its light curve, but in its power to hold a mirror to our own hopes, reminding us that the most compelling mysteries are those that allow room for both rigorous data and boundless wonder. The search for answers in the cosmos often feels like a slow, patient process, but some mysteries announce themselves with a sudden, deafening roar. In 2007, astronomers sifting through archived data from the Parkes radio telescope in Australia found something that should not have been there. It was a burst of radio waves so powerful that it saturated the receiver, a blast of cosmic energy that lasted for just 5 milliseconds. If all the energy released by the sun over several decades were compressed into that fleeting instant, you would have a fast radio burst. These are not the gentle whispers of a distant star, they are the universe screaming at the top of its lungs. The initial discovery was so bizarre that researchers spent years ruling out terrestrial sources, from earthly electronics to satellite glitches. But then more were found by other telescopes confirming their extragalactic origin. These bursts are traveling from galaxies millions, even billions of light years away, and in that millisecond flash they outshine entire galaxies. The first great division in this mystery is between the repeaters and the one-offs. Most fast radio bursts are singular events, a catastrophic bang that happens once and is never heard from again. But a handful of sources defy this rule. They erupt again and again, firing off bursts with no discernible rhythm or pattern. Some remain silent for weeks, only to unleash a frantic storm of a dozen bursts in a single hour. This repetition is a crucial clue, ruling out any theory that involves the complete destruction of the source, like a star being torn apart by a black hole. So what cosmic engine can produce such unimaginable power on a millisecond timescale, and then have the fuel to do it over and over? The prime suspect for the repeating bursts is a magnetar, a type of neutron star with a magnetic field so intense it defies comprehension. These fields are trillions of times stronger than Earth's, and when they undergo a starquake, a sudden cracking of the star's rigid crust, they could potentially unleash a focused beam of radio energy powerful enough to be seen across the universe. This theory gained significant traction when, in 2020, a magnetar within our own Milky Way galaxy was observed producing a radio burst that, while weaker, shared striking similarities with the extragalactic signals. Yet, for the non-repeating bursts, the plot thickens. The leading theories point to even more violent one-time events. The collision and merger of two neutron stars is a strong candidate, a cataclysmic event that warps spacetime and could release a final, concentrated shriek of radio waves as the two ultra-dense objects spiral into each other. Another possibility is the blitzar, a hypothetical phenomenon where a supermassive neutron star, temporarily stabilized by its own rapid rotation, suddenly collapses into a black hole when it slows down, causing its outer magnetic field to be severed and releasing a tremendous burst of energy. But the mysteries only deepen from there. Even if we identify the general type of object, the precise mechanics of how it creates a fast radio burst remain elusive. What is the exact trigger for a magnetar's starquake that results in such an energetic release? How can some sources produce bursts with such wildly different energies and patterns? And perhaps most perplexing of all, we have begun to detect something even stranger within the bursts themselves. Some show a bizarre effect where the lower frequencies of the burst arrive at our telescopes noticeably later than the higher frequencies, a phenomenon that cannot be fully explained by the simple dispersion caused by interstellar gas. This suggests the bursts are traveling through an incredibly hot, turbulent plasma, an environment we do not fully understand. Fast radio bursts are more than just cosmic fireworks, they are probes. As these fleeting signals travel across the vast, empty spaces between galaxies, they pick up a fingerprint of all the material they have passed through. By studying them, we are not just learning about the bursts themselves, but also mapping the invisible, diffuse matter that makes up the cosmic web. Each millisecond burst is a message in a bottle, hurled across the void by forces we are only beginning to comprehend, carrying with it the secrets of the most extreme environments in existence. The violent energy of fast radio bursts illuminates the most extreme events in the cosmos, but one of the most profound mysteries in science hits much closer to home. It is a puzzle written not in distant starlight, but in the oldest rocks on our own planet. This is the faint young sun paradox, a contradiction that threatens our understanding of Earth's very origins. Billions of years ago, when life was first taking hold, our sun was a much weaker star. Astrophysical models show it was only about 70% as bright as it is today. With that much less energy reaching Earth, our planet should have been a frozen ball of ice, a global snowball with no liquid water at all. Yet the geological record tells a completely different story. We find evidence in ancient rocks of flowing water, of riverbeds and oceans, from a time when the planet should have been locked in a deep freeze. How could a world under a faint sun have been so warm and wet? The answer seems to lie in the air itself. Scientists point to a supercharged greenhouse effect, a blanket of atmosphere far thicker than today's. The prime suspect is carbon dioxide, a powerful greenhouse gas that could have trapped the sun's feeble heat with remarkable efficiency. If the early atmosphere contained much higher concentrations of CO2, perhaps hundreds of times greater than current levels, it could have provided the necessary insulation to keep the oceans liquid. Other theories propose that methane, an even more potent greenhouse gas, played a leading role, possibly produced by early microbial life forms, but each solution introduces new complications. If CO2 levels were that high, we would expect to see certain chemical fingerprints left in the ancient rock record, evidence that is often missing or ambiguous. A methane-rich atmosphere would have created a different set of problems, potentially leading to a hazy, organic smog that might have actually cooled the planet instead of warming it. The paradox deepens when we consider that the warming mechanism had to be exquisitely balanced. It needed to be strong enough to prevent a global ice age, but not so powerful as to trigger a runaway greenhouse effect that would have boiled the oceans away, turning Earth into a hellscape like Venus. This delicate balance suggests a complex, interacting system where geology, chemistry, and perhaps even early biology worked in a fragile concert to regulate the planet's temperature. The exact recipe of gases that created this planetary coat and the feedback loops that maintained it for over 1 billion years remain one of the most active and unresolved questions in paleoclimatology. It forces us to ask whether our planet's habitability was a lucky accident or the inevitable result of a system that knew how to keep itself alive. The faint sun that warmed our infant Earth revealed a universe that was, on the grandest scales, meant to be a featureless expanse. The cosmological principle, a cornerstone of modern science, insists the universe has no center and no edge, that it should look the same in every direction, a perfectly mixed cosmic soup. Yet, when we examine the oldest light in existence, the cosmic microwave background, we find a potential crack in that foundation. Astronomers have discovered a strange and unsettling alignment they have dramatically nicknamed the axis of evil. This is not a malevolent force, but a puzzling correlation between the subtle temperature fluctuations in this primordial light and the plane of our own solar system. In essence, the universe's background radiation seems to know which way is up for us. The hot and cold spots in this ancient glow are not scattered entirely at random. There appears to be a preferred direction, a kind of cosmic spine that aligns eerily well with the ecliptic, the flat disk in which Earth and the other planets orbit the Sun. This is profoundly unexpected. Why would the grand structure of the entire universe, imprinted at the moment of its birth, share any geometric relationship with our tiny, local cosmic neighborhood? The immediate and most comfortable explanation is that this is a colossal statistical fluke, a trick of the data. Perhaps our methods of processing the signal from satellites like Planck have inadvertently introduced this pattern, a systematic error that creates an illusion of alignment. Scientists have combed through the data searching for just such an artifact, and while some potential biases have been identified, many argue the anomaly persists even after accounting for them. If it is not a fluke, the implications are staggering. It would mean the universe is not isotropic, not the same in all directions. We would have to confront the possibility that our location in the cosmos is not average, that we occupy a special place with a special viewpoint. This would force a fundamental rethinking of cosmology itself, potentially requiring new physics to explain why the universe has a built-in directionality. One radical theory suggests the alignment could be a remnant from before the Big Bang, a fossilized imprint of a previous cosmic era whose structure somehow set a preferred plane for our entire observable universe. Another, even more mind-bending idea is that this correlation points toward a universe that is far from smooth on the largest scales, perhaps even finite, and with a complex topology that we are only glimpsing. The axis of evil stands as a quiet, humbling reminder that our most cherished principles about the cosmos are not immutable laws, but working models, always subject to revision by the next, deeper look into the void. Even our own moon holds onto its secrets with a stubborn glow. For centuries, astronomers have documented strange, fleeting events on its surface, known as transient lunar phenomena. These are not the slow, predictable changes of shadows, but sudden flashes of light, mysterious patches of color, and unexplained hazes that appear and vanish in minutes or hours. The reports are numerous and credible, from professional observatories to amateur astronomers with their eyes glued to the eyepiece. They describe pinpoint flashes bright enough to be seen from Earth, and vast areas that momentarily dim or take on a reddish tint. This is not folklore, it is a persistent visual mystery happening right next door. The most logical explanation points to outgassing. The moon is not entirely geologically dead, and it is possible that pockets of radioactive gas like radon are occasionally released from beneath the surface. When these trapped gases burst into the vacuum of space, They could kick up fine dust that scatters sunlight, creating a temporary shimmering cloud or a localized bright spot. Another straightforward cause is meteorite impacts. The Moon has no atmosphere to burn up incoming space rocks, so even small pebbles strike the surface with tremendous force, creating a brief, brilliant flash of heat and light upon impact. These events are regularly observed and documented, yet other theories venture into more exotic territory, such as electrostatic phenomena. The lunar surface, constantly bombarded by solar wind, can build up powerful electrical charges. Some scientists speculate that this static electricity could suddenly discharge, levitating dust into glowing clouds or creating a phenomenon similar to an immense, silent lightning strike in the vacuum. The fundamental problem is not a lack of theories, but a lack of consistent, conclusive evidence. These events are, by their very nature, transient. By the time multiple telescopes are trained on the location, the glow has faded, the color has vanished, and the Moon has returned to its silent, gray normality. We are left with a collection of compelling anecdotes but no smoking gun. This makes transient lunar phenomena one of the most visually accessible yet deeply debated anomalies in our celestial backyard. It is a reminder that even the most familiar object in our night sky can still surprise us, flickering with a mystery we have witnessed for hundreds of years but have never been able to truly grasp. The flickering glow of our own Moon highlights the mysteries in our celestial backyard, but if we pull our gaze back to the grandest scales of the cosmos, we find a different kind of anomaly, one defined by an almost terrifying absence. Drifting through the constellation of Boötes lies one of the largest voids ever discovered, a spherical region of space so empty it has been called the Great Nothing. This is the Boötes Void, a cosmic desert spanning an almost unimaginable 330 million light-years. If you placed our Milky Way at its center, we would be utterly alone, with the next major galaxy so far away it would be a faint, lonely speck in a sea of blackness. The existence of such a vast emptiness directly challenges our models of the universe's structure. According to our best theories, matter after the Big Bang should have clumped together in a relatively even web, with dense galaxy clusters connected by filaments and separated by moderately sized bubbles. The Boötes Void is not a bubble, it is a chasm. It is far larger and far emptier than any simulation predicts, suggesting that either our understanding of the initial conditions of the universe is incomplete, or that some unknown physical process carved out this colossal hollow. Yet this desert is not completely barren. Scattered across its immense volume, astronomers have found a handful of isolated galaxies, like a few lone trees in an otherwise endless expanse of sand. These galaxies are themselves deeply peculiar. They tend to be old, red, and quiet, with very little of the star formation activity we see in galaxies within clusters. It is as if they are relics stranded in this void for billions of years, their development stunted by the profound isolation. They had no neighboring galaxies to collide and merge with, no fresh inflows of gas to fuel new generations of stars. They are fossils of a quieter, lonelier universe. The very presence of these galaxies deepens the mystery of the void's formation. Did the void form around them, leaving them behind as the rest of the matter flowed away? Or were they somehow flung into this emptiness, destined to drift in solitude? Their strange, quiet nature offers a unique laboratory for studying how a galaxy evolves when it is cut off from the cosmic mainstream, showing us a path of stellar life that is rare and isolated. The Boötes Void stands as a monumental question mark, a silent challenge to our maps of the cosmos, reminding us that the universe is not only filled with brilliant structures, but also with profound and puzzling emptiness. The profound emptiness of the Boötes Void speaks to a universe of startling extremes, but another limit, one written into the very laws of physics, appears to be breaking right before our eyes. This is the GZK cutoff, a theoretical barrier that should make the universe a cosmic prison for the most energetic particles. The theory proposed by Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin dictates that ultra-high-energy cosmic rays, protons traveling from distant galaxies at nearly the speed of light, should not be able to reach us from beyond our local galactic group. Their journey should be a short one. The space between galaxies is not completely empty. It is filled with the faint glow of the cosmic microwave background, the relic radiation from the Big Bang. When a proton with unimaginable energy slams into one of these background photons, the collision is so violent it creates new particles, sapping the proton's energy until it falls below the theoretical cutoff. It is like a marathon runner trying to sprint through a field of dense, sticky mud. They will be slowed to a crawl long before the finish line. This means that from sources billions of light years away, only lower energy particles should ever arrive at Earth. Yet they do not. Our observatories have repeatedly detected cosmic rays with energies so immense they defy this fundamental limit. These are not just slightly energetic particles. They carry more kinetic energy than a professionally thrown baseball, all compressed into a single subatomic proton. The fact that they exist at all is a paradox that cuts to the core of modern physics. How do these cosmic speedsters complete their journey without losing their punch? One possibility is that we are misjudging their origins. Perhaps these ultra-high energy particles are not coming from the distant universe at all, but are generated much closer to home within our own galactic neighborhood. If their source is relatively local, they would not have had to travel far enough through the cosmic microwave background to be slowed down. The challenge here is identifying what natural particle accelerator within our galaxy or local group could possibly be powerful enough to create such staggering energies, as our known astrophysical objects do not seem to fit the bill. Another explanation points to our understanding of the particles themselves. Maybe these are not protons, but heavier atomic nuclei like iron. A heavier nucleus has a different interaction with the background radiation and might, in theory, survive a longer journey with its energy somewhat intact. However, the data from observatories like the Pierre Auger Observatory is increasingly pointing toward a proton composition for at least some of these events, which only deepens the contradiction. This leads us to the most thrilling and unsettling possibility that we are seeing the fingerprints of new physics. The GZK cutoff is a prediction firmly rooted in Einstein's special theory of relativity and our well-tested knowledge of particle interactions. To see it violated means that one of these foundational pillars might have a crack. Perhaps at these extreme energies, the laws of physics behave differently. Maybe Lorentz invariance, a key principle of relativity, breaks down, allowing particles to travel just a little bit faster or interact differently than our models predict. Or perhaps there is a completely unknown type of particle that does not interact with the cosmic background in the way a proton does, allowing it to travel unimpeded across the cosmos. Each ultra-high-energy cosmic ray that strikes our atmosphere is a messenger from the far reaches of space, and its very existence tells us that our map of the universe's most basic rules is still incomplete, waiting for a new discovery to redraw its boundaries. If the Boötes void is a cosmic desert, then the constellation Coma Berenices holds a ghost. There, 100 times fainter than our own Milky Way, drifts a galaxy called Dragonfly 44. At first glance, it seemed unremarkable, a wispy, ethereal smudge of light so diffuse that astronomers initially overlooked it. But when they measured the motions of its sparse collection of stars, they found something impossible. Those stars were moving at ferocious speeds, orbiting so quickly that the feeble gravity from their own visible mass should have been utterly incapable of holding them together. The entire galaxy should have flown apart millions of years ago. The only explanation was that Dragonfly 44 is anchored by an immense, invisible source of gravity. This galaxy, as wide as the Milky Way, is 99.99% dark matter. It is a cosmic phantom, a skeleton with almost no flesh, a gravitational monster cloaked in near invisibility. Its discovery shattered the assumption that dark matter and visible matter are always partners in a predictable dance. We thought dark matter was the scaffolding upon which galaxies were built, with the amount of visible stars and gas roughly corresponding to the amount of dark matter pulling it all together. Dragonfly 44 breaks that mold completely. It has the dark matter halo of a colossal spiral galaxy, but only a tiny, pathetic sprinkling of stars. How does a galaxy acquire such a massive gravitational anchor and then fail so spectacularly at the business of making stars? One theory suggests it is a failed galaxy, a dark matter cloud that, for reasons unknown, never accumulated enough ordinary gas to ignite widespread star formation. Perhaps it was born in a barren region of the cosmic web, starved of the raw materials needed to shine. Another, more violent idea is that it was once a normal galaxy, but its gas was brutally stripped away in a traumatic encounter, leaving only the resilient stars and the indestructible dark matter behind. This ghostly galaxy forces us to ask what truly defines a galaxy. Is it the stars we see, or is it the invisible gravitational heart that holds it all together? The hunt is now on for more of these dark galaxies, these celestial phantoms hiding in plain sight. Finding them is like trying to spot a whisper in a hurricane, but each new discovery helps us map the shadow universe of dark matter. They are pure laboratories for studying this mysterious substance in isolation, free from the complicating glare of normal matter. Dragonfly 44 is a stark reminder that most of the cosmos does not glow, it merely gravitates, and its silent pull is what truly shapes the universe we see. This ghostly galaxy is a world of pure gravity, but our own solar system holds a storm of impossible complexity. Above the scorching surface of Venus, a colossal double vortex spins in perpetual motion at the planet's south pole. This is not a single, simple whirlwind like the hurricane of Jupiter, but a vast, shape-shifting figure 8, a pair of connected eyes staring out from a world of crushing pressure and acid clouds. It is a dynamic monster capable of changing its form in less than a single Earth day, a meteorological puzzle wrapped in a toxic shroud. While Earth and Mars have their own polar vortices, they are relatively stable cold core systems. The Venusian vortex is a hot, violent, and deeply unstable phenomenon, born from the planet's super-rotating atmosphere, where hurricane-force winds whip the entire cloud deck around the globe in just 4 Earth days, a pace far faster than the planet's own sluggish rotation. This creates a turbulent flow that funnels down toward the poles, twisting and collapsing into this bizarre, double-lobed structure. The fundamental mystery is not just its strange shape, but its persistence. Why does this chaotic system maintain its general form for years at a time, even as its internal structure writhes and contorts? What forces prevent it from simply dissipating or merging into a single, calm whirl? The thick, hostile atmosphere of Venus is the very reason this mystery remains so stubborn. Our probes cannot survive for long in that corrosive, high-pressure environment. The European Space Agency's Venus Express orbiter gave us our best data, watching the vortex from above, but it could only see the cloud tops, a two-dimensional view of a deeply three-dimensional event. We are like doctors trying to diagnose a patient's internal illness by only looking at their skin. We see the vortex breathe and morph, but we do not know the engine driving its heart. Is it powered by heat rising from the planet's surface, or by turbulent eddies feeding energy down from the faster-moving mid-latitudes? Does the intense solar heating at the cloud tops play a role in stabilizing its bizarre form? Scientists create complex computer models to simulate the Venusian atmosphere, but replicating the vortex's rapid shape-shifting and long-term stability has proven incredibly difficult. Every model that gets the shape right often fails to capture its chaotic motion, and vice versa. This tells us we are missing a key ingredient in our understanding of fluid dynamics under such extreme conditions. The Venusian vortex is more than a local weather pattern. It is a laboratory for the physics of thick, super-rotating atmospheres, a swirling, acid-laced signature that our sister planet still holds its secrets close. From the swirling vortex of Venus, we travel back to the very first minutes of the universe, to a problem forged in the heart of creation itself. The Big Bang was not just an explosion, it was a cosmic forge, a brief, searing moment when the entire universe was hot and dense enough to fuse the first atomic nuclei. In those first few minutes, protons and neutrons collided to form the universe's first hydrogen, helium, and a tiny, trace amount of lithium. This process, known as Big Bang nucleosynthesis, is one of the pillars of modern cosmology. Its predictions for the amounts of hydrogen and helium match what we observe in the oldest stars with stunning precision. But for lithium, the numbers are catastrophically wrong. Our best models predict about 3 times more lithium-7 than we actually find when we look at the ancient stars in the halo of our galaxy. This is the lithium problem, a small number with enormous implications, a crack in the foundation of our origin story. How could the universe's first recipe be so right for 2 ingredients and so wrong for the third? Cosmologists and nuclear physicists have been wrestling with this question for decades. One possibility is that our understanding of the nuclear physics itself is incomplete. The rates of the specific fusion reactions that created lithium in the primordial soup are incredibly difficult to measure in laboratories on Earth. Perhaps a key reaction proceeds at a slightly different speed than we currently believe, enough to reduce the final lithium yield. Another, more exotic solution points to new physics beyond the standard model. What if unknown particles, like certain types of dark matter, were present in those first moments? These particles could have interacted with the primordial soup, altering the balance of protons and neutrons or providing a new pathway for nuclear reactions, effectively destroying some of the lithium as it was being born. Then there is the stellar possibility. The oldest stars we use as cosmic fossils have been burning for billions of years. Could they themselves be the culprits, somehow destroying lithium in their interiors over their long lifetimes? Astronomers have indeed found that some stars can drag surface lithium down into their hotter cores, where it is torn apart by nuclear fusion. But the oldest, most pristine stars are supposed to have preserved the original chemical composition of the universe. Finding a mechanism that consistently depletes lithium in all of them, and by exactly the right amount, has proven to be a massive challenge. This tiny discrepancy is far from a trivial detail. It is a crucial test for our most fundamental model of the universe's birth. If the problem lies in nuclear physics, we must refine our understanding of how matter behaves under the most extreme conditions. If the answer requires new particles, we might be on the verge of a discovery that reshapes particle physics. And if the solution is purely astronomical, it forces us to completely rethink how these ancient stellar fossils evolve. The lithium problem is a quiet but persistent alarm bell, reminding us that our story of the cosmos, for all its success, still has missing pages written in an element we have yet to fully understand. The universe's recipe may be flawed in its smallest details, but some puzzles suggest the entire cookbook is wrong. We now venture into one of the most speculative frontiers of physics, a concept so strange it is known as unparticle physics. This idea proposes a hidden sector of reality, a shadow realm where the very notion of particles breaks down. In our standard model, everything is made of distinct particles with specific masses and properties. Unparticles would be different. They would not be particles at all, but rather a substance or a field that behaves as if it has a fractional, fuzzy mass, appearing more like a continuous, non-particulate fluid flowing through the cosmos. This is not just a new particle, it is a new state of matter operating under entirely different rules. The motivation for such a radical idea comes from gaps in our understanding that current physics cannot fill. Certain subtle gravitational anomalies, for instance, defy neat explanation. We see tiny, unexplained tugs on galaxies or energy discrepancies in high-energy cosmic events that dark matter and known particles do not quite account for. What if these are not just missing pieces, but whispers from this hidden sector? Unparticles could interact with normal matter only through gravity or exceedingly weak forces, making them nearly invisible to our detectors. Yet their gravitational influence could subtly warp spacetime in ways that leave a unique signature. Imagine the gravitational pull of an object that does not have a defined location in the way an atom does, but instead exists as a diffuse, scale-invariant presence. Its gravity would not follow the clean, inverse square law we expect from planets and stars. It would be a ghostly, smeared-out force, potentially explaining why some cosmic structures seem to have extra gravity that does not cluster in the way dark matter should. This is the tantalizing, if highly speculative, promise of unparticles. They reside in the liminal space between established science and theoretical fantasy. No experiment has yet confirmed their existence, and the evidence is purely circumstantial, buried in statistical anomalies and theoretical equations. Yet, the very fact that such an idea can be seriously debated by physicists highlights a profound truth. Our understanding of reality is a map, and anomalies like these are the first signs of undiscovered continents lying just beyond its edges, waiting to be charted. These 25 cosmic puzzles reveal a universe far stranger and more wonderful than we ever imagined. From the fleeting whisper of a single radio signal to the silent pull of a ghost galaxy made of dark matter, each anomaly is a testament to the vast unknown. They are not simply errors in our data, but signposts pointing toward the edges of our understanding, reminding us that our most cherished scientific models are living, breathing ideas, constantly challenged and refined by new discoveries. The true value of these mysteries is not in the answers they provide, but in the questions they force us to ask. They are the engines of science, driving us to build better telescopes, to question fundamental laws, and to peer ever deeper into the void. So the next time you find yourself under a clear night sky, look up. Remember that each point of light is part of a grand cosmic story still being written, a story filled with inexplicable geometry, invisible forces, and silent, watching giants. The universe is inviting you to be curious. What space mystery captivates you the most? Share your favorite cosmic puzzle in the comments below. And if you are hungry for more journeys into the unknown, be sure to subscribe. The cosmos has only begun to share its secrets.